Okay, wow, what a week. We're all back. A few things real quick. The home page has been changed, so hopefully everyone's had a chance to look at that. Let me plug in here and so you can see it. And so on the home page now, I'm going to put the assignments and when they're due and what problems there are. We may have to modify a little bit because of the hurricane. We'll see how that works out. Let me find my thing here. As far as assignments and stuff like that, I know people are going to be behind. Things are going to happen. Just because we're all back doesn't mean everything is kosher. So if you run into any problems with anything, just let me know. It's not a big deal. Okay. Questions on anything before we get started? I want to pick up where we were last time, which is on continuity. Before I do that, I want to kind of review, because in 2.7, we're going to try to bring everything together. So let's just take a minute and review. So what we were saying was, in calculus, we have long-term change and short-term change. All right, so we have short-term and long-term. And we said, whenever we're thinking about short-term change, we're always thinking about the rate of change. We're thinking about how the function changes as we change the independent variable, how quickly as it changes. And so this led to this picture that we're going to come back to in 2.7. So we said, okay, we can talk about a function. Maybe it's the distance function. And we could talk about how much that function is changing over an interval. So if you were driving when you evacuated, right, you could have two time points. Maybe you leave at 12 o'clock, an hour later. You see how far you traveled. And that's, of course, the speed. So we talked about the average rate of change on an interval. On T1, T2. Okay. And we said that this was a slope of the secant line. We thought about this geometrically. But that was easy. That's kind of a high school rate of change. What we're really interested in is the instantaneous rate of change. What's the velocity at a single point? You're driving along and you see a cop, right? And you want to know, right this minute, what is my speed, okay? And so the way that we got around that, kind of the genius of Newton was that he realized physically it made sense. We couldn't do it mathematically, but really explain. He realized that physically it made sense. That as that time interval got smaller and smaller and smaller and smaller, that average rate of change was approaching. And so we saw that geometrically, as we moved this point, T1 to T2, what happened was the secant lines morphed into the tangent line. And so we had this notion that the instantaneous rate of change at T1 was the limit as T2 approaches T1 of f of T2 minus f of T1 over T2 minus T1. This was the instantaneous rate of change. And that motivated the need for us to take limits. And so then we went through all this stuff about limits. How do we take limits? We could do graphs. We could do tables. We saw that all of those had complications. Sometimes when we make a table, we can't tell exactly what the correct value is. Sometimes it has functions like sine of 1 over x. And we can't really use the graph as x approaches 0 to evaluate that limit. So then we come up with all these limit laws. And this really motivated the need for continuity. Okay, it isn't so obvious why we're switching gears. We're talking about average rates of change, then we're talking about limits, now we're talking about continuity. But the beauty of continuity is that it lets us evaluate these limits. Because if a function is continuous at a point, so this kind of motivates the need for continuity. Because if a function is continuous at a point, we evaluate the limit by substitution. That's it. So we say if f is continuous at x equal to a, then the way we evaluate this limit is we simply substitute. And that's why continuity, one of the reasons, there's three reasons why continuity is important. That's why we always use functions continuous. Because if it is, the limit is trivial. The plot is a graph, just plug the value. And that's continuity. So how do we use this? So let's kind of go back and talk about a few things that we were talking about last time. So there are a couple of rules. If you look at the part 2 and part 3 of the notes for 2.5, they're basically giving you a bunch of rules that people sat down, looked through rigorously. We're not going to do it, but they're rules that we can always use. So they're the main rules that you have to know about continuity, or there are three main rules. Three rules of continuity. Okay. Rule 1 is that every function that you know of, there are weird functions, but every function that you work with is continuous in its domain. In other words, if I have a function and I can plug a value of x in and I'm not doing anything mathematically illegal, it's continuous. So I'm going to say all. It's not really all because there's tons of functions, but all the ones that we know, okay? So all functions are continuous in their domain. That's the first one. Okay, the second thing, composition of continuous functions. And this rule is a little slippery because it says a little bit more than that. But compositions of continuous functions are continuous. So we have to be a little careful. Here's what that actually says. It says that if we have two functions, well I'll let you read it. This is theorem 9 in section 2.5. But here's what the theorem says. And the import, and what I really want to draw on is what's going on. Let's just think about this. If G has to be continuous like that. So as x approaches a, G of a approaches G of a. Now you can square it. Composition of continuous functions are continuous. And so this is actually it's theorem 8 and theorem 9. I'm not going to deal with theorem 8. Okay, so what's happening is x approaches a, because G is continuous here, G of x approaches G of a. And f has to be continuous at G of a. It's like, it's literally a limit within a limit. X approaches a, G of x approaches G of a, f of G of x approaches f of G of a. But this is a useful theorem. What's really useful, though, is that we have to learn how to recognize compositions. So there's a notion of an outside function here, right? It's the thing we do last. It's literally positioning on the outside. There's an inside function. How do you recognize a composition? When you look at a function, and it's not a known function, because the inside of that function is something nasty, that's a composition. That's how you recognize a composition. We're going to come back to that. The last rule is some really nice rules that says basically any sort of algebraic combination we could think of, sums, differences, products, quotients, okay, of continuous functions are also continuous. With the caveat that if you have a fraction, that denominator cannot be approached. So this is, I forget the theorem, but it basically says that algebraic combinations of continuous functions are continuous. And those are things that we want to use. Notice how important the form is. This notion of being able to distinguish between composition and algebraic combination. Algebraic combination is really important. Concentrating on algebra is really, really key. When we do integration, and we do U substitution, when we do derivatives, and we do the chain rule, recognizing the form is going to be crucial. So it's a good idea, and it's going to help you right now too. So there's a lot of payoffs to doing that. All right, any questions on what we've been doing up to this point? So I want to pick up and go back a little bit, just back up a little bit and talk about this example. So this is the notes from 2.5, and this is part 2. And I'm on page 2. So it's the notes that starts, actually it's part, hold on, let me make sure I have the right one here. Actually, it's part 3, so it's the notes that start off like this. And so we said that when we have algebraic combinations, we don't want to move to the difference, because when we have algebraic combinations, which are important of continuous functions, we want to find out the domain that all of those functions are continuous. And so what that means is we're going to take the intersection of all the domains. So when we have algebraic functions, or algebraic combinations, the intersection of the domain of all of those functions. When we have compositions, things are a little bit different. So here's a problem I want to look at. I want to evaluate the limit as x approaches 1 of the arc sine of the ratio 1 minus square root of x over 1 minus x. I'm not taking the limit of just the regular function. I'm not taking the limit of 5%. Is this a product? What is the So you have to be careful. So there's actually a couple of things going on, right? So there is a ratio. I know how to deal with limits of ratios. So I have a ratio inside of here. But notice that's not going to get me the whole function, right? So you're right. This is a ratio. But I still got to deal with this guy. And I want to kind of look at it. Unfortunately, no, because the arc sine is the inverse sine. It takes the inverse function, right? Sine takes an angle and gives you a value between minus 1. Arc sine goes backward. It takes a value between minus 1 and gives you the angle. So the inverse function of a square is square root of 1. So I'm going to say it's a composition. My outside function is the arc sine, and the inside function is that mass relation. I'm going to say this is f. My arc sine is my function f. It's my outside function. And if you don't mind, I'm going to use sine to the minus 1 because I think it's not saying I'm taking the reciprocal, but it's the inverse sine, okay? I'm going to write it like this. So this is my f, and this is my inside function. Okay? And it's the arc sine of another function. It's not a bad idea to test yourself. How can I test to make sure that's true? Well, I could substitute this in and see, right? I'm claiming that f of g of x is equal to the inverse sine of 1 minus square root of x, 1 minus x. Well, this is f of what is g of x. Okay? And this is equal to f is inverse sine. I'm putting a question mark here. I'm not sure if that's true or not. But sure enough, when I substitute it in, just substitute your function again. Okay, so now I have a problem. If this function was continuous at 1, and this quantity, the limited one, gave me a value of minus 1 and 1. I could use That's not going to work. So what I'm going to have to do is I'm going to have to use theorem 8. So theorem 8's a little more subtle. It says the inside function doesn't have to be continuous, but the limit has to exist. So theorem 8 is saying that the limit of g of x has to exist. So let's go ahead and look and see how this is going to work. Okay, so the first thing I notice is that I have a composition of functions. The bad news is that the inside function is not continuous. It's not continuous at x equal to 1. So what I'm going to hope, I'm going to try to use theorem. This is I can't use theorem 9. Let me try it out. But I'm going to try to theorem 8. The theorem 8 can ask does the limit. If it does, I'm okay. So what we want to know now, so this says no theorem 8, no theorem 9, sorry. So the next thing I'm going to do is I'm going to check and see is the limit as x approaches 1 of the inside function. Does this exist? And if it does, I can use theorem 8. So the question is, how do I evaluate this thing out? The question is, everyone pretty much nailed it. It's a relation. So that's the idea. How do I evaluate this? I put in the value or have a better thought. And the next thing I do is back is I have a square root. The equivalent of square root, I'm going to try to rationalize. So I multiply that by the conjugate, and I'll let you go through all the gory details. But when you get done, so what that means is I'm going to multiply by the same quantity, but I'm going to put a positive sign, that's the conjugate. And I claim that when you do this and all the mathematical smoke clears, you're going to get 1/2. This is I'm going to leave this as an exercise. So the conjugate on the top of the bottom, 1 times square root of 1 times square root. I'm giving it 1/2. past level 1. Right? We got past the inside. What about the outside? So the limit does exist. I might be able to experiment. And let me just stress that when I do this problem, I have to do it. I have to call it. It's the process. It's not a function. Okay? You try this, it doesn't work. So what do I know now? I was hoping to fix it. It wasn't. Okay. What can I do now? Use experiment. Yes. But this still might fall apart. Okay? Because what has to happen now? Now I have to make sure is sine of minus 1/2 defined at 1/2. I know arc sine is continuous where it's defined because it's continuous. So now you can see the inverse sine of 2, right? Yes. In other words, the inverse sine of 1/2 is the sine of that angle. What is that? This is our pre-algebra, right? So I'm going to claim, I'm going to leave this as an exercise to you. I'm going to claim, if we go back to our unit circle, okay, that should be what? 30 degrees, 60 degrees, 90 degrees. Sine is the, so this is 30 degrees, or we say it, or we say it the grown-up way, pi over 6. It's pi over 6, it's also 5 pi over 6. I'm going to leave this as an exercise for you to figure out. Now, are those the only values? Why not? Too high. So how do we write that? So this is a little tricky. So I'm going to say that the final answer, the limit as x approaches 1 of inverse sine of is equal to pi over 6 plus 2 pi n and 5 pi over 6 plus 2 pi n, where n is just any integer. And so this is the limit. It's pi over 6 plus 2 pi n and 5 pi over 6 plus 2 pi n. When you're working with inverse trig functions, you always have to take into account the periodicity, and you have to be careful because different trig functions are periodic. But this is kind of the process. This is what we want to go through. Now, when we're taking the compositions, okay. Sometimes it's easy to figure out where the function is not. So what I'm going to do is, notice I have a composition here. My inside function is x squared. The outside function is sine. So what I'm going to do is composition I look at. And I say, oh, great, we have a sine. As soon as I see something like that, I know it's a composition. So the first thing I'm going to ask is, are there any values that are so what we notice is that the inside function is continuous for all x. All polynomials are continuous. The next question I have to ask myself is, are there any outputs of x squared for the sine? So, are there any values of x that can I square the sine? So when I look at the outside functions, I notice that, so the question I ask here is, are there any values of x so that x squared will not be in the domain of sine of x? And the answer is no. You pick any number you want. So I have what? A composition of continuous functions. So what is the point? What do I do now? The value of the composition. So what do I do? So I want to go, are there any values of x so that when I square this number, this so here's the deal. And I have a video account. But what I know now is that I have a complicated substitution. Right? I'm just going to substitute. And well, in this case, I'm sorry. I wanted to say where are the following functions continuous? So these are continuous everywhere. I don't have a limit. So this function is continuous everywhere, and this is my answer, which is nice because then if I have a limit, I could evaluate. Okay, so this is a good one to do because this actually will have a problem. When you look at the inside function, I'm moving down to the x. So look at the inside function. But you're going to have a problem when you get to the log because you're going to ask the question: are there any values of x because the argument will not be the domain of the natural law? The answer is yes. The natural law will be the domain of all positive conditions. But when cosine x is minus 1, we have 1. And then have to those steps. So I'll let you work this out, but I will tell you the answer. So the problem is that 1 plus cosine x can be negative 1 at x equal to, gotta go back and think, it's odd multiple to pi. Odd multiple to pi. This is 2n plus 1. These are odd multiple to pi. And so because of that, the natural log won't be defined there. It's not continuous. So these will be the points for which natural log will not be defined, and the composition will not be defined. Natural log will not be defined. So this is why I said inside and outside. When you write the next function, inside function, that's the other one is actually a very output. The value of x because the output is inside function, not These are good to practice. If I have time, I'll put up a practice quiz for you because I want to make sure you know this well. All right, I said there were 3 reasons for continuity. Here's the second one. This is a really nice application. It's probably going to be value for you. And what it says is if you have some function that's continuous on closed interval, that closed interval part is really important. It's a finite closed interval. So f has to be continuous on a finite closed interval. There are intervals that are closed but not finite. Then there's something really cool we can say. We can say, okay, if you look at the value of f of a and you look at the value of f of b, they're defined by the interval. There has to be some value of x or f of that value. And that's why it's called intermediate. I'm looking at any value, just only the value of two inputs. If it's any intermediate y value, there has to be a value of x. Why does it work? I'll tell you very, very briefly. Based on a fact from the game mathematics, if this game happens, what is the value? So there's one mathematics that says, think about value theorem, we won't worry about the y, okay? But here's one of the applications. It's very useful. And I'll just point out really quick. If you need value theorem, you don't say there has to be one. You can try it. You can draw and that's not a trivial observation, because here's how we use the intermediate value theorem. We use it for root solving. So very often, you know, we use the formula for that. What is the formula? There's actually a formula for that. What is the formula? Well, that comes out of that. It's very unfortunate, but it's a really cool result. So there is no general formula. So what do you do? So what you do is you have a situation like this. And you know, by the way, this is a cubic. There is a formula. Has anyone ever used this formula? This is really complicated. Nobody wants to do it. Okay? So how do we show that there's a root in here? Well, let's look at the function. So I'm going to look at. So first of all, everyone agrees this is a continuous function, a polynomial, continuous everywhere. I'm going to look on the closed interval 1 to 2. I'm going to evaluate f of 1. Let's see. So that's going to be 4 minus 6 plus 3 minus 2. So that's going to be what? Minus 2 plus 1 is minus 1. Function going down here. And now I'm going to look at f of 2. And so I'm going to have 4 times 8 minus 6 times 4 plus 3 times 2 minus 2. So I'm going to have 8 plus 4 is that. So I have the function here is minus 1 at the lower endpoint. It's going to be positive 12. And I don't really care about the value. All I care about is the function. And so So this is my intermediate value 0. Intermediate value, for instance, yeah. There's definitely one here. There might be more. I don't know. What are we talking about? How do you find it? The easiest way is to do bisection. So how would bisection work? I'll just show you this really quick because it is fun. What I would do is I would start at 1.5, and I would evaluate f of 1.5. And what would I see? I would see if it's positive or negative. Okay? It happens to be positive. I'm not going to compute the value, but it happens to be positive. Now, which interval would I search on now? Okay? I have an interval 1, 1.5, 3.5, 2. Well, the 0 has to be in this interval, right? Because I know you're in the problem. Whatever the sign, right? And so I would look here. I would do the same thing. I would cut that in there. And figure out the sign. Very naive, inefficient way that all the signs do is the plan of the table. That's called a bisection. It's not in the homework, it's not tested on it, but it is cool. All right, any questions on continuity? Okay. So the last thing we want to look at is how to evaluate limits at infinity. So this is 2.6. And I want to come back to something that people have talked about. So we talked about asymptotes. You have vertical asymptotes. Vertical asymptotes are infinite limits, right? As x equals approaching a, f of x is approaching either positive or minus. The vertical asymptote is going to be infinite. What we're going to talk about is horizontal asymptotes. There's actually 3 asymptotes, right? There's vertical, horizontal, we're going to talk about those too. So here is a limit at infinity. Notice the word. This is saying as I go to infinity, as x goes to infinity, f of x is equal to 1. And what that means is that you tell me, this is like the discrete point. What are we talking about here? This point is this f of x is equal to 1. And when you think about it, you're talking about how. That means f of x is equal to 1. I think it's close to all of that one. So you say, okay, I want to include this thing draw this thing. And what I have to do is go to change the size. I have to do it. That x value was over. So these are just horizontal asymptotes, and you can see the graph is doing what? It's prediction, right? X goes to infinity. What is that x doing? So for our purposes, intuitive understanding will suffice. You don't have to get into the details. Now, and I'm not going to deal with this. You can kind of look at this and think about this a little bit. The big question is, how do we evaluate limits at infinity? And what's going to happen is we're going to have very often ratios. And of course, you can make tables. Okay, you can make tables in this. Tables really are tables we saw in So here's how we're going to think about ratios. This is going to be the hard part. So you could make a table, you could make a graph, and see what's happening as x approaches infinity. But you'd be surprised, some of these graphs are really, really smooth. These graphs are not so long as that. You really have to go way out because it grows really slowly after a long time. So we want to do it the right way. And the book goes through a lot of a lot of, I think, a rather complicated explanation. So in part 2, basically, what I want you to understand is the fact that actually, I could do it this way, but I would rather not. I could leave it this way, but I'm going to do this. So what we're going to use is the fact that 1 over x to the r. Actually, you know what? I do want to leave it that way. I do want to leave it that way. So when r is positive, this limit's going to be 0. So 1 over x to the power. The idea is that r is positive as x goes to infinity, x to the r is going to infinity, which means 1 over x to the r is going to go to 0. And this is actually true. So let me go ahead. I am going to change this. Let me do it this way. This is equal to infinity if r is greater than 0. These are the only 2 factors that really have to know. You have positive power, so this is the graph. And the graph of this looks like this. So now we have something really nasty looking. Right? We have the limit of some ratio of that curve. And what we do is we look at this called the least term in the numerator and the denominator. So what I'm going to do is I'm going to look at the numerator and I'm going to ask, what is the highest power of x? Okay? And it's x squared. That's called the leading term. And I'm going to do the same thing in the denominator. So this is the leading term in the numerator. And also x squared is the leading term in the denominator. Right here. Right here. And it just happens at both squares. I'm just going to ignore everyone else. So I'm going to write this like this. I'm only going to put in the leading terms now. I like that. X squareds cancel. My answer is the other side. You can also divide. If you want to do a little you can drop all the terms except the leading term, or so the idea is I'm going to drop all the terms except the leading terms. But if you want to do it a little more old school, you can divide by the leading term of the denominator. Okay? You can also divide by the leading term of the denominator. which means I'm dividing by x squared. So if I want to take my time about it, I'm going to get 3x squared over x squared minus x over x squared minus 2 over x squared. I'm dividing everything by x squared, top and bottom. 5x squared over x squared plus 4x over x squared plus 1 over x squared. Smoke clears, you're going to get this. I'm just going to cancel out x's. 3 minus 1 over x minus 2 over x squared. 5 plus 4 over x plus 1 over x squared. So as x goes to infinity, all of these guys, their limits go to 0, and you did the same thing. So let me do one example with roots, and I'll let you do this. Actually, we want to show that this is infinity. Change that to infinity. So if you go through the same rules, you can convince yourself that this limit is not 0. It's infinity. I'm going to leave that as an exercise. So what if we have something like, let me do a hard one here. I'm going to go to the third part of the notes. Because roots are really going to have problems. So let me ask you a question. What is the extension of the same thing? What is the root of part 2? Well, I have to So I have to use the fact that the square root of t is really t to the 1/2. And if I use laws of exponents, right, I'm going to get t to the 3/2. So I'm going to rewrite this like this. The limit as t goes to infinity of t minus t to the 3/2 over 2t to the 3/2 plus 3t minus 5. Okay? Take off the leading term. Leading term is over now. Larger exponent, right? Larger exponent, I'm just going to make them right? I just forget about those. Keep my minus 1, you gotta be careful. And I'm going to end up, I just drop all of the other terms, and I get the limit as t goes to infinity of minus t to the 3/2 over 2t to the 3/2, and that's going to be minus 1. What do we do now? What do you think we do? Because if I have this here, okay, what's there? No, it's actually x cubed. It's exponent, Drop all the way down. All that's the way of looking at it. You can do that. Yeah. So this is hard. If you have any questions on this, let me know. I think this is a little harder. So